Oh, hello, old friend. It's good to see you. Let's talk about this word, fascination. It describes an unquenchable urge which compels our hearts to quest and be captivated. As long as there are elegant explanations to complicated phenomena, science will never lose its romance. Over the years, I've traveled the world, indulging in my fascination in physics. And now, I find that a new hunger has woken within me. A fiery need to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my titanium physicists. You're listening to the Titanium Physicists Podcast, and I'm Ben Tippett. And now, allez, physique!
In classical computation, there are problems which are described as hard. They're problems which require exponentially more time to solve, the more complicated the problem starts out as. So they're usually problems which require you or the computer to look at every single possibility so that you can compare their outcomes. My favorite such problem is called the traveling salesman problem. So imagine you have a salesman, and he has several cities that he needs to visit. He doesn't know which order he needs to visit the cities in order to make the shortest possible travel time. So if there are 3 cities, there are 6 possible orders that he could visit the cities in. So you'd have to calculate the travel time for 6 different routes, and then compare them to see which is shortest. But if there are 4 cities instead of 3, there becomes 24 different orders he could visit the cities in. And if there are 5 cities, there are 120 different orders he could visit the cities in. So the computation time required to find a solution is enormous because you need to do one calculation at a time. Now, there's a type of computer which has the capacity to do all of the calculations at once. And it does so by harnessing the weird power of the laws of quantum mechanics. These quantum computers might end up giving us a way to solve some of the hard computational problems in efficient amounts of time. Today, we're going to be talking about the subtlest and nerdiest of machines, the quantum computer. Now, speaking of things both nerdy and subtle, there is a lady on the internet who's made a name for herself for her insightful and entertaining reviews of nerdy movies and books and stuff. She's the Empress of Geeks. She has her own YouTube channel with hundreds of thousands of subscribers. She has cool pink hair and a boxy robot friend. You can find a link to her videos on our website. It's Comic Book Girl 19. Welcome to the show, 19.
Hello.
Okay, 19. For you today, I've assembled 2 fantastic titanium physicists. Arise, Dr. Katherine Brown.
Hello.
Dr. Katherine got her PhD from the University of Leeds and has just finished a postdoc from Louisiana State University. Now arise, Omair Taibah.
Beep, 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 beep.
Omair got a degree in electrical engineering and physics from King Fahd University of Petroleum and Minerals in Saudi Arabia. He's currently applying to graduate school, and we met when he sent me an email a year ago asking to do a show on this very topic. All right, everybody, we're going to be talking about quantum computers. So, to talk about quantum computers, we need to start by talking about how quantum mechanics means that objects act in different ways than we're used to. Omair, why don't you start by telling us about the double slit experiment?
So let's imagine we have a cannonball shooter, and we have one slit in front of it, and we shoot the balls through that slit. On the other side of the slit, we can imagine a pattern, which is basically just straight ahead from it. Nothing will change the trajectory of the cannonballs. But now, let's imagine we have a box filled with water, and we have like a barrier with one slit into it. And right after that, 2 slits. So there are 2 barriers, and when we make a wave from one end, the wave goes through one barrier and one slit, and it goes in a certain pattern.
Uh-huh.
Let's imagine now that we have two slits. Each wave will go through one slit, and then on the other side of the barrier with two slits, we'll have a certain pattern that goes up and down on the surface of the other end of the box.
Okay.
So what happens is that in the cannonball, we shoot at objects. In water, we make waves. Now we know that light is some type of a wave, and if we do the same experiment with two slits, it has a pattern similar to that made with water.
Okay, I'm with you.
So now let's do it with electrons. There was a time when we thought they are objects, like balls. So if we shoot them towards those two slits, lo and behold, we find a pattern similar to a wave. So this made us think about electrons differently, that they possess some type of wave characteristics.
Okay.
So if we cover one of the slits, so it's one slit, we find the pattern goes completely like the one we had when we shoot cannonballs.
Mm-hmm.
So this experiment tells us two things. The dual nature of electrons, it's an object and a wave at the same time. And the other thing that it tells us, that there's a superposition, that the electron actually passes through both slits at the same time.
Right. So the idea is that, like, if you take water, just regular wavy waves, and you put them through a double slit and then have a wall behind it, the waves will interfere with each other. They'll hit the wall with different phases depending on where along the wall you are, and so sometimes the wave will be really high and where it'll be really low. And essentially, if you take an electron gun and you shoot it at a wall with two slits in it, if you look one at a time, the one electron won't come in with a wave, but the one electron might come on really high up the wall or right in the middle. And so if you shot a whole bunch of electrons through, the sum of electrons will end up interfering with each other, and you'll see these fringes. So it'll look just like an interference pattern on the back wall. And the deal is you say, okay, maybe one electron is interfering with another, the way two water waves will interfere with each other. So the deal is that if you cover up one slit, if you shoot one electron, you'll see it travel essentially along a straight line. But if you open two slits that it could pass through, what happens is the single electron will end up somewhere else on the wall. It won't follow a straight line. Instead, it will end up in one of the fringes. It'll just kind of show up in the middle or way up high or something like that. So the question is, what has deflected this electron? And the answer is, somehow the electron splits into two pieces. One of the pieces goes through the upper hole, the other piece goes through the lower hole, and then they recombine on the back wall. And the location they'll end up recombining is defined by these interference fringes.
Okay, so it splits into two pieces, right? So these two pieces, they come back together on the back wall? Like, are they like magnetized back together? How does that work?
It's important to note the electron doesn't split in half and one half go through one slit and one half go through the other slit. The way we think of it, and it's not intuitive and it won't be, is the whole electron is going through both slits at once.
Yes.
Okay. If you do an experiment and begin looking at it, so if you put a little detector at each slit to work out which slit it's going through, and you begin firing, you fire a single electron, and you wait a while, fire another single electron, you'll find your distribution will have a pile of electrons opposite one slit and a pile of electrons opposite the other slit. Mm-hmm. So if you observe which one it's going through, it behaves exactly like you're firing a cannonball through two very big slits. There really isn't an intuitive answer, I'm afraid.
That's what I've been hearing. I was told about the quantum computer over dinner one night, and I guess I should just tell you guys what I know about it, which isn't very much because I really appreciate physics and especially quantum physics, but it just always goes over my head. So what I heard was regular computers are binary and they only have, ones and zeros. There's only two different things, whereas I heard a quantum computer works on 32 different levels instead of just two, like a binary computer. And I also heard that it was made a company in Canada and that they just started building parts and seeing what worked. They didn't know how they were doing it. They just were like, well, let's see if it works. And apparently they built it and it works, but they don't really know exactly how it works.
There's some things you got right, 19, and some things that it doesn't quite line up.
Okay.
So the first thing you said was that the difference between a quantum computer and a regular computer is that in regular computers, they have bits, right? All the information is stored as zeros and ones. And in a quantum computer, things are stored in these kind of quantum packets called qubits, the quantum bit. And the thing is that these qubits obey the laws of quantum mechanics. Specifically, they obey the law of superposition.
In qubits, remember the analogy of Schrodinger's cat?
So we got the cat and we've blocked him in a box and we can't observe anything in the box. And also in the box there's a particle, so we've got a quantum system. And what we have is, after, say, 10 minutes in the box, the particle has exactly 50% chance of decaying. And so, as far as we know, the particle is in a superposition of decayed and not decayed. It's both at the same time. Until we observe it, it's impossible to say if it's decayed or not. It's somewhere between decayed and not decayed.
Okay.
Also in the box is a vat of poison. And if the particle decays, it hits the vat of poison, releases the poison and kills the cat. Mm-hmm. If it's not decayed, the poison's fine, still locked in its little vat, and the cat's alive. And so what you've created here is a kind of large-scale quantum superposition. You've created this cat that's equally alive and dead.
So the idea here is that, so if we're going to talk about qubits, all things in quantum mechanics aren't kind of described in terms of certainties. They're described when we're not observing the system. The system acts like all of these different possibilities are essentially happening. It's kind of like when we were talking about an electron going through both slits at once.
Yeah.
There were two possibilities. The electron goes through the top slit and the electron goes through the bottom slit. And if you can't tell where the electron is in the intermediate time, technically the two different possibilities evolve independently of one another, as if they were both the only one kind of that existed, right? So the electron possibility that would go through the top slit goes through the top slit. The electron possibility that it goes through the bottom slit goes through the bottom slit. And then when it hits the back wall, those two kind of interact. So in quantum mechanics, the deal is we'll have these qubits, and one of them is 0 and the other is 1, and we can evolve the system as if they're existing independently of one another. Instead of having to do each calculation, a series of calculations that start with the bit being 0, and then it's restarting and starting a series of calculations that start with the bit being 1, we can treat the system like it's both, do them both at the same time.
Mm-hmm. Okay, so with a quantum computer, essentially, you're creating two different realities same time.
Well, for every different qubit, there's two different realities.
Okay.
So if we have like 2 qubits, that's 4 realities basically. If we have 3, that's 8 different realities that we're calculating at the same time.
So how many qubits are in a quantum computer?
That's an engineering question.
I think it's important to make clear, if you imagine your qubit is either in 0 or 1, although you can be in the superposition of 0 and 1, so 50% 0 and 50% 1, you're never in half. You're always in 50% 0 and 50% 1. I know that's really counterintuitive example, but you're never in some number between 0 and 1. You're always in some probability of being 0 and some probability of being 1. You only have the two states. You don't have the things in between don't really exist. It's very discrete.
It's kind of like, imagine you had a friend who was very cowardly, and you know that he was kind of a subtle thinker, and so you asked him whether he was going to vote for Republicans or Democrats, say. So in his head, he might say, well, the Republicans have this advantage, and the Democrats have this advantage, and they would weigh the two options. And so if you could rip open his head, you would say 30% Republican, 70% Democrat. But if you ever asked him his opinion, are you going to vote Republican or Democrat, he'll never say 70% Democrat, 30% Republican. He'll always either say Democrat, 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 Republican. And so the only way to gauge that he's 75% Democrat is you just have to ask him over and over and over. I mean, you have to, let enough time go by for him to go back to his, some state where it's mixed. And then you ask him, and it's always going to be one or the other. But if you ask him enough time, if you do enough trials, you can get a sense of what the statistical layout is.
Okay, I understand. That makes sense.
I know it's a bit early to be answering this question, but how many qubits make a quantum computer? And I think it's a bit of a debatable question at the moment. D-Wave, the Canadian firm, have 514, I believe, roughly quantum things. It might be slightly different from that, but around 514. And they can solve at least one problem. But their quantum computer is not a fully generalized quantum computer, or at least at the moment we don't believe it is. So you can't solve all these problems that people want to solve on a quantum computer on this D-Wave machine. For a fully generalized quantum computer that can solve any quantum algorithm, the best people have is somewhere between about, at least I know they have had 10 and they might be on 15 now. And they've used it, I believe, to factor 21, but they were cheating. So they were cheating because it's easier to factor something when you know the answer, which sounds really obvious, but you can do a simpler calculation if you know the answer, and they used the fact they knew the answer to do the simpler calculation. And another paper has demonstrated actually using this cheating technique you can factor using coin toss. But at the same time, they are showing you can do all these gates, and they do have a universal machine, even if it is too small to run. Particularly useful algorithms.
So the deal is that when you want to make a quantum computer, there are a variety of techniques that you can use to build a quantum computer.
Okay.
Essentially, when you want to build a quantum computer, you need to take advantage of some quantum aspect of something you can engineer. Quantum computing, it's kind of like you're doing experiments with Schrodinger's cats. If you observe the system, your cat goes from being 50% alive, 50% dead to either 100% alive or 100% dead. You collapse the wave function. So on the one hand, if you're interacting with the system too much, you'll interfere with the quantum superposition. All of the different possibilities won't evolve the way you're expecting them to if you poke the system too much. So it's fairly fragile. But on the other hand, you need to interact with the system a little bit, because if you don't interact with the system, and you're not doing really any computation. And in quantum computation, what you're doing is you have all these qubits, and you're kind of evolving them in an appropriate way to do a computation. And so you need to manipulate the system without poking it too hard. So it's a very fragile problem. And actually, when you poke it too hard and you interfere with the system, that's called decoherence.
Well, isn't like I said, I was told that the people who built the computer that is supposedly works, they don't really know how to explain it exactly. They don't even know exactly how it works. Is that a true statement?
They aren't telling the public how it works. But certainly if you buy one of the machines, it comes with full circuit diagrams of what it's supposed to do. 2 have been sold. One was sold to Lockheed Martin and is currently at USC. USC have done some work characterizing it, and at the moment they say it's probably operating on a quantum level, but they're not convinced by the idea that it actually gives a speed up. So they're not convinced it's better than your laptop. Actually, they were comparing to algorithms run on your laptop, so we're not even talking compared to a supercomputer. And the other one's bought by NASA and Google, and that's more recent, so people haven't had the chance to work on that one yet.
So we don't even know for sure if the quantum computer works, or is it an actual quantum computer yet?
No, we don't. I would imagine the people at D-Wave have a very good idea what their machine's doing. Part of the difficulty is, and when we talk about quantum computing with you, we talk about a model of quantum computing that's very much like your classical computer. So in your classical computer, you imagine your bits of 0 and 1, and you're doing gates on them, so AND gates, OR gates, NOT gates. And in your quantum computer, you have a different set of gates, but they're equivalent to AND or NOT. But what they're doing is a model of quantum computing called adiabatic quantum computing, which has actually been proved to be universal. If they have a full adiabatic quantum computer, which we don't know they do. If they did, it would be universal, barring the fact that you can't do error correction yet. But people are working on that. What happens in adiabatic quantum computing, it's if you make a system very, very cold, it goes to its ground state of energy. So it has the lowest possible energy levels possible. So I'm trying to think how to explain.
Okay, there's this thing called Heisenberg's uncertainty principle, and the deal is if you're talking about a particle, you can't know what the momentum of the particle is and know its location to arbitrary accuracy. So the deal is the more you know about the momentum of the particle, the less you know about where it is. There's a fundamental constraint on how much information you can know about a particle. So if you confine a particle to a little region, like you put it inside a box, you've got like a little shoebox, and you take an electron and you put it in and you close the box. Suddenly, you know a lot about where the particle is. You might not know exactly where in the shoebox it is, but you know that the particle isn't outside the shoebox. And what this means is you're also constrained about how much you know about the particle's momentum. So the natural consequence of this is that anytime you take a particle and it's constrained spatially in any way, it's going to have some minimum amount of energy associated with it. There's always going to be a minimum amount of momentum that you can assume that it has just by virtue of this Heisenberg principle.
Okay. Electrons never stand still.
They never stand still. They're always wiggling a little bit.
If you look at the hydrogen atom, you have a proton in the center and then you have an electron orbiting the proton. I used to think that the electron was orbiting it and it could take any position roughly orbiting it. But what we found instead was it was actually in a set number of levels. It was either in level 1, level 2, level 3, level 4. And this was represented how much energy the electron had. And if you give it more energy, it could go from level 1 to level 2. But it could never exist between level 1 and level 2. You had to give it at least enough energy to get up to level 2.
Okay.
And so the ground state is when the electron's in its lowest possible state. So we'll say level 1. And we can extend that up to a really large system. So we can imagine a system of lots of electrons or lots of different systems. And they're all down so that they're in their lowest possible energy level.
Okay.
And what happens in adiabatic quantum computing is you can take your computer to the lowest possible energy level for the standard interactions for your computer. So your computer has an equation that's natural for it. There's a natural set of interactions between the qubits in your computer. And you can take it to the lowest possible energy level for this set of interactions. If you then very, very, very slowly, with very little energy, begin slowly trying to change the system, so it's kind of simulating another system, you can do this and keep it in the ground state. So you can find the ground state of your other system. And the D-Wave machine, we know it can find the ground state of its system, and it can do that very well. And what they hope it will be able to do is be an adiabatic quantum computer so that you can slowly apply energy and change the ground state to the ground state of a different system. Say you've got your hydrogen atom and you slowly apply energy so it feels like it's acting like a helium atom. So that's the idea. You're trying to change it to act like another system.
Okay.
And if they can do that, then it will be a universal quantum computer. So it'll be able to do all the problems we want. The problem with it is even if we can do that, at the moment, it's not fault tolerant. So what that means is one error and your computer just gives you a completely random answer. It can't cope with a single fault. And we don't think there's any form of error correction. So if there's one error, we have to just start again. We can't get rid of that error. Mm-hmm. In the circuit base of quantum computers, where we're further behind because we've only got these 10 qubits, we do know how to define whether a system is fault tolerant and how to correct an error. So that's the advantage of that system. So D-Wave have done a lot of things that are very promising, but they're not at the point of having this wonderful universal quantum computer that you can go out and solve the factoring problem, which...
Okay, so we mentioned at the very start that computer science classifies different problems in terms of whether they're hard or not. And a hard problem is one that dramatically increases the computational time as you incrementally increase the difficulty of the problem. So I started out by explaining the traveling salesman problem, which is probably not, you probably actually can't use a quantum computer to solve it any more efficiently than a regular computer.
Traveling salesman's on definitely can't, actually. I think they've proved it's impossible. But
So when people first started talking about quantum computers, it wasn't clear that they were any better than normal computers. And then somebody came up with a way, there's this one really famous hard computational problem, this factoring problem. So when our computers, we're on a secure website or something, when we're trying to do secure communications, our computers kind of encode all the information. In essence, there's a really big number that's exchanged. And this number is two prime numbers multiplied together. If I asked you to tell me which two primes multiplied together give you a certain number, it's tricky, right?
Yeah.
It gets increasingly difficult. So, for instance, 6, not that hard. It's 3 and 2. If it's 10, not that hard. It's 2 and 5. If it's 34, you start having to go through all the different primes before it to see which ones multiply together to get that one. And so essentially, it's kind of like the traveling salesman problem. It's computationally really, really difficult. It takes a ton of resources, and the higher up the numbers get, the larger the number of possible primes that you need to look at that can multiply to get that one.
Okay.
So what they need is a system of cryptography where the bank, say, can release a key which you can use to encrypt the data, but you can't use to decrypt the data. And that's the idea behind the encryption using primes. The idea is you use this big number that's the multiple of the two prime numbers to encrypt your data, but you can only decrypt the data by knowing what the 2 prime numbers were. So that's just putting it in context of where it's coming from.
So the deal is with quantum computers, it was shown in the 90s that you can use quantum computers to crack this problem in non-exponential time. In essence, the larger the number doesn't necessarily dramatically increase the amount of computation time to figure out what those 2 primes are. So if you've got one of these working universal quantum computers, all this cryptography we're using is in essence just bunk, because somebody gives you a really large number and you put it in your quantum computer, and it takes advantage of the fact that you can use the superposition principle to calculate multiple possibilities at once, and then it spits out your answer and it can tell you what the 2 primes are without having to wait,
Right.
your entire lifetime.
So what you'll be relieved to know, given that if this problem was solved, bank encryption wouldn't be secure anymore, is the D-Wave machine isn't believed to be able to solve the factoring problem, and I haven't heard any claims from D-Wave that they can.
So, all right. One question I have is I was helping put together a computer because I have little hands. Seeing what goes into a regular computer, what kind of parts go into a quantum computer? Are they the same type of parts? Are they completely different type of parts? Like, what is on the inside of this?
So in a quantum computer, it depends a bit on what you're using. So, for example, you might use an ion. So an ion is an atom with 1 electron missing, so it's got a charge. And it's sitting in a magnetic trap. The magnetic trap uses a magnetic field to trap the ion in place. And your quantum computer would be a row of all these ions all trapped in place. Where it's different from the classical computer is in the ion trap, at least, your little qubits, your ion, would never move. You'd use lasers, so you can imagine it's now very difficult for your classical computer, because these traps aren't small. They're massive, probably taking up a large portion of a table, if not more, for 1 qubit. And you shine lasers on them to move them up or down and interact them with each other. Another alternative, and it's the one that both me and Omair have the most experience with, would be the idea that you use a single particle of light, so a photon, as your computer. In this case, your operations would be done using wave plates that change properties of the photon. To some degree, they're a bit like the glass you use in a 3D cinema, which are polarizers. So you can use things like that, and the photon will then travel at the speed of light through your computer, going through all these different types of plates, which when you see them physically, they look like thin sheets of glass, but they actually all do something. The photons are very difficult to interact with each other, and to do that, you use detectors. So you have to generate the interaction using detectors. And the detector, it's very difficult to make, and they're fairly big things that normally, to get a good result, have to be cooled down to 2 or 3 Kelvin temperatures. So the quantum computer might look like that. Some quantum computers are basically rows of diamonds. The diamond's made of carbon atoms, but sometimes it's not very good and you have a little error in it, and they can build quantum computers using these errors in the diamond. So at the moment, there's very different ways that they look. But short of some work being done in Bristol University where they've got the photons on small chips, your quantum computer is significantly bigger. It's taking up lab tables, which are the size of a fairly big dining table. It's probably being cooled to 2 or 3 Kelvin.
You can get shit that cold?
Yeah, your quantum computer is probably very, very, very cold. So obviously, you can't touch things at that temperature. You're probably using lasers to control it, unless you're using a quantum optical system. So you're going to be having a lab bench with masses of equipment and lasers. The D-Wave machine is a chip, but it needs to be cooled down. So when you see their machine, it's basically inside what is a giant fridge, which is a black box that says D-Wave on, and apparently inside is a tiny little chip that does all the calculations.
Okay, your computer has to be in a fridge to use it. So what the hell kind of operating system do you use? What do you put Windows on there? I mean...
At the moment, D-Wave have their own programming language. Some people I've collaborated with have come up one for your gate-based quantum computers, which is called Quipper. But you're probably still very close to running, you know, the idea of application, so where you're programming on the level of the architecture of your computer, you have no higher level things to help you.
Okay, so you have to code like everything in yourself.
Yeah.
Well, I'm never going to use one of these quantum computers then, because I can't do any of that. Okay, so NASA bought one and Lockheed Martin bought one. So what are they going to do with these computers? Like, what problems do they need this computer for? I mean, are they just testing it really to see, or are they actually going to be using it to help them with ridiculous problems?
I'll answer the questions in 2 bits. So first of all, you say you'll never use one, but we have to remember we're still vaguely at the stage, if you go back to valve computing, so classical computing, before they invented the transistor. And you'd never use a valve computer because it's big, it doesn't have a good system to run. But that doesn't mean that it's never going to have a good operating system that runs. It just doesn't have one at the moment because we're still at the very basic valve stage.
Okay, well that gives me hope then.
Lockheed Martin gave the computer to USC, which is University of Southern California, and they've been characterizing it. I don't know if they intend to use it for anything else. NASA and Google do have some plans, but we're not sure what they are at the moment, so there will be some studying of it. And one thing you can do on a quantum computer is you can get an improved unordered search. You can't get the wonderful improvements in factoring, you can't get the exponential improvements, you can only get a quadratic improvement. But it has the advantages you don't need a universal quantum computer, they can be done on simpler computers. So there is the possibility that Google might be looking at it for that reason, but that's not coming out of Google. My old boss, Jonathan Dowling, feels that's what they're likely to be using it for. But this isn't something that I've heard from either NASA, Google, or D-Wave themselves, so it's idle speculation.
Okay. So, besides D-Wave, is anyone else trying to make these guys, or are they kind of the only game in town?
I've read about Mike Lazaridis, former CEO of BlackBerry, RIM, investing in the University of Waterloo, and I've read about Toshiba, I think. They're trying to do one. I think there are a lot of teams that are trying to make one, but there are many ways to approach how to make a quantum computer. And each way has its advantages and disadvantages. No one knows really which one would be viable for commercial quantum computing.
That's something that I really enjoy about the idea of the quantum computer, that there isn't just one way to do it. There's like a million different ways to do it. And that's what I find really interesting about all this is, I don't know, there's like so many different ways to do one thing, which is really cool in my opinion. Well, like how close do you think are they to making a universal quantum computer that really works? Like, in your guesstimation, how many years will it take to where we can have a real one that works?
These small models that Bristol and several other universities, they are universal in the context that if you had a 10-bit quantum computer, you'd have a universal 10-bit computer. So you've got the universal computing, you just haven't got the size that you need. It's going to take a while, I think, before we have something that can do something that your classical computer can't. And at the moment, we don't think D-Wave have that. And I think it's going to take a long while, and it's going to take a lot more than the 1,000 qubits that they have. Part of the disadvantage is quantum systems are a lot more prone to errors than classical systems. And you can get around this. The simplest error correction is the idea that you can encode 1 qubit in 3 qubits. So you can use 3 qubits to represent your 1. And that continues. So you can, at the next level, each of those 3 qubits can be represented by 3. So you use 9 qubits to represent your 1. And in fact, one of the most famous uses 7. But what you find is each logical qubit, so each thing you're operating on, has got to be encoded in hundreds to thousands of physical things to get our error rate down. And so that's a big problem with building it, is you can't get your million qubits and compare it to a million qubit classical computer. You need to be doing this error correction all the time.
So a quantum computer is kind of like a person because they can be wrong sometimes.
Yeah.
Okay, so what types of problems, like say NASA, like what types of problems would they solve with this computer? Like would they start solving like crazy space flight problems and things like that, or would it be more...
So the most famous one is the one Ben mentioned, which is factoring. You also get some improvement on sorting an unsearched database. Simulating a quantum system is believed to be a big one. They'll be able to simulate other quantum systems, maybe simulate superconductors better. In idle speculation on what I think might come out, there might be improvements in simulating fluids. I believe that might be the case, but there's no proof of that yet. There's a lot of abstract mathematical problems that they can solve with improvements. I mean, there are problems which do have, particularly you'd want to look for these ones which have the exponential improvement, as we explained, of factoring, because they're the problems that your classical computer won't be able to solve as you get more powerful classical computers. Anything with a less than exponential improvement, your classical computer is going to keep improving for a few years, so there's a chance that your classical computer will get there. But writing the algorithms is difficult because, so what we went back and we said is on your quantum computer, you can process all the options at the same time. So if you're running it on 0, 1, 2, 3, you can process 0, 1, 2, 3 at the same time. But as soon as you do a measurement, you collapse it into the state of either the answer for 0, 1, 2, or 3. So it becomes very difficult to write an algorithm because you have to think very carefully how you're going to get the data out. So I think with bigger improvements on data extraction procedures, and there are some very good ones at the moment, it'll be nice to get more that give you a wider variety of data that you can extract.
So wait, we're not even smart enough to ask the right questions to this computer?
I guess that's a way
nice.
to say it.
That's a nice way to put it, yes.
Yeah.
That's really interesting.
Yeah, that was fun. Thank you, Katherine. Thank you, Omair. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit, Katherine. You get a kumquat.
Nom 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 nom.
And Omair, you get a quince.
Yum, 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 yum.
I'd like to thank my guest, Comic Book Girl 19. Thank you, Comic Book Girl 19.
Thank you so much, Benjamin. Thank you, Katherine and Omair. You guys were really helpful.
This was a fun discussion.
If you want to know anything more about quantum computing, my former boss, Jonathan Dowling, has just published his book, Schrodinger's Killer App, Race to Build the First Quantum Computer, and I can tell you it's incredibly funny. So check it out.
All right. Hey, TIE Fighters, listen. I know you love the show, and I love hearing from you. If you'd like to interact with the Titanium Physicists, there's a variety of ways. Why not follow us on Twitter at Titanium Physics, or you can join our Facebook group. If you'd like to hang out with us and socialize, why not join our online forum? The Brachio Board is a fun place where fans of the Brachio Media Network gather to chat about science and things. Or if you'd like to send me an email directly to ask a question or propose a topic, email me at barn@titaniumphysics.com. Or if you'd like to tell me nice things, email TIEfighter, TIPHYTER, at titaniumphysics.com. I'm always happy to hear nice things. Okay, that's it for the main part of the show. Remember, if you like listening to scientists talk about science in their own words, you might also want to listen to other shows on the Brachio Media Network, like the weekly Wienersmith, where Kelly and Zach Wienersmith talk to academics about their research, or Science Sort of, where we talk about science in the news, or Technically Speaking, where they talk about engineering. Editing support for the Titanium Physics podcast is provided by a gentleman named John Heath. Thanks, John. You're doing a bang-up job. The intro song to our show is by Ted Lewin and the Pharmacists, and the end song is by Jan Vanderslice. Until next time, my friends, good day, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
And so it's kind of illustrative here to start with Schrodinger's cat. It's kind of an overused metaphor. When we got our quantum mechanics textbooks as undergraduates, they had these beautiful gold embossments on the front, the fake leather covers, and on the front there was this stripy cat, and it was alive and looking playful. And on the back it was asleep. And the deal was that it was Schrodinger's cat, and the back cap, it was dead. It's delightfully overused, the Schrodinger cat joke. So the deal is that Schrodinger was kind of interested in how the macroscopic world was different than the microscopic world. He was different in demonstrating how the way we talk about quantum mechanics is a little bit absurd. So he said, here's a macroscopic object. It can look at things. It's alive. It's conscious. It's a cat. And we put it in a box. If that box is isolated from the rest of the universe, if we can't observe it, if we can't interact with it, then we have to treat the physics, what happens evolving inside the box, according to the rules of superposition. So there are two different possibilities. One where the atom decays and the cat gets poisoned and dies, and the other where the atom doesn't decay and the cat stays alive. And so functionally, until you open the box, the cat is both alive, there's a possibility where it's alive, and there's a possibility where it's dead. And so both possibilities are existing simultaneously until you open the box and see for sure.
Well, where does this number 32 come from? Because when I was talking to this guy, he was telling me, the binary, and then he was saying the quantum is 32. Is that because it's 10 qubits? Is it like from that? Like you were saying that the computers have 10 to 15 qubits right now? And is the 32 different, I don't know. Where does that number come from? Do you guys know what I'm talking about?
Never heard the idea of 32 levels or anything like that related to quantum computing. I mean, it might be a 32 times speed up. They might have been, one of the D-Wave articles might have been promising that, on a particular problem. I'm wary of constant speed ups anyway, but we can go into that. We'll go into that later so you can understand what I mean. But no, I've not heard the number 32 mentioned, particularly special in the field.
Okay. Yeah, I was wondering, the reason I bring it up is because, in the Kabbalah, there are 10 spheres, of like there's like 10 spheres here, and they're connected by 22 pathways, and that allows for 32 different states of consciousness. And I was wondering if there was any sort of connection there, because I know that quantum physics is a really weird world, and that's like, I love the place where, science and philosophy, religion, like consciousness, like weird stuff like that, like things get really weird in there. And so that's why I'm asking. Because I was wondering if there's any sort of connection.
There are some people in the field who believe that the brain might be a quantum computer, particularly Roger Penrose. There are a lot of arguments against it that I would say which make me on instinct disagree with him. If we look at when we're trying to create our quantum computer, what we need is a system that's very isolated from its environment. It's often very cold. We're cooling it down using liquid nitrogen or even colder sometimes. And what we have in our brain is a very noisy, messy environment. So it seems very unlikely that you could get quantum coherence maintaining itself in the human brain, just because of the physical conditions we need to create quantum computing. We need to create quantum systems. There are some people investigating quantum biology, but it's still a very vague field, and there's still a lot of work in it that is more idle speculation than science. It's not actually backed up by science. And again, it's because we get to this problem that it's very hard to understand how a quantum system can exist in this noisy, hot environment, because that's ideal for decoherence. When we try and create an artificial quantum system, we can't, or create a system that's operating on a quantum level. Noisy, hot environments are dreadful. You can't get anything. It's probably quite good because it explains why our world operates on a kind of classical level than a quantum level in the big scales. But it does, I'm very cynical about the idea of quantum consciousness. But if you do want to read that, I think Roger Penrose is the main person who understands quantum mechanics who's pro it.
Okay. All right, everyone was talking about artificial intelligence and the robot uprising. So would an AI, like, would it be like you could actually make like a robot that feels something? Like, would a quantum computer, would that be an even more dangerous, like, Terminator robot? Or would it be about the same dangerous Terminator robot?
There is quite, speculations about that when it comes to quantum computers. I've read a lot about, and I've heard a lot about when at some point quantum computers will reach to unity with humans and
yeah, I'm definitely interested in all that sort of stuff, and like Ray Kurzweil and all this crazy futurist stuff that he's always talking about. Like I was saying, the quantum computer, it sounds like kind of like a person in a way where it can be wrong and it can, think about certain things and whatever. So would that be more, of an environment where an AI would actually like learn to feel and do things like that versus like on a regular computer.
The thing is, in AI, like in computer learning, even in the classical computer, we know exactly how we do it. The computer actually learns little by little. In quantum computer, we just don't know. The algorithms we have are very limited to specific problems.
I think one way to think about it is that, like, if you want to build a robot that's as smart as a human, you need to make it really fast at computing. The feeling will be in the software. The quantum computers are more than just really, really fast normal computers. They're good at solving different questions. It's like you said, we don't even know what kind of questions it'll be good at answering. But it's good at the type of questions where you need to ask it to do a whole bunch of computations at the same time to suss out all the different possibilities, rather than trying to figure out the linear type of computing that we normally use our computers for. So it's not clear to me that a quantum computer would be any better at emulating a person with its feelings, unless you wanted to make a computer that was really uncertain and unreliable about the decisions.
Well, that's most people. I don't know if you know anything about that.
Answer the question in two parts. Firstly, I think the idea of all the quantum error correction algorithms, apart from one, have actually come from classical error correction algorithms. So people, once upon a time, classical computers were as bad as quantum computers, and people were developing error correction for them. And the second point, I think, with the AI that's fairly interesting, as pointed out, obviously, is that years ago, people used to say that once we have a computer that solves chess, we have an intelligent thinking computer. We now have a computer that can beat a world expert in chess, yet we wouldn't consider it an intelligent thinking computer. So what we're finding, or at least this is certainly what Scott Anderson's suggesting, and it seems to be reasonably true, is that we keep changing our requirement to define a computer as an intelligent thinking machine like human beings. And I'm not sure at what level that's going to change. Obviously, it's possibly slightly sad, but you can see transcripts of people hitting on an AI that is basically functioning at a fairly low level. And there's some transcripts, even in one of the books I was reading, that, yes, when we have a computer that we can't distinguish it from a human being in conversation, which is the idea of the Turing test, when we do have that, which we're like, I think we will have, are we going to define that as an intelligent thinking computer, or are we going to be like we are now with chess and just say, no, of course a computer that can play chess isn't an intelligent, emotional, reasoning machine?
Well, if I can have a conversation with it, then it's a lie.
Yeah.
I will treat it as a thing. I don't care if it's modern. But I'm also very sensitive towards robots, I guess. I don't know. I grew up with Data from Next Gen, and I always felt bad for him. You know? He's just like you. He's just not made out of, flesh. It's okay. Well, okay. So this is another question I have. This question for you guys, all three of you. What are you most what about the quantum computer excites you? Like, what are you pumped about?
Well, to me, I really like quantum communication, which is fairly related, actually really related to quantum computing. And that's what excites me personally the most. Because
what is quantum communication? What is that?
That's a whole new tangent. But basically, it's using the same concept of quantum mechanics to communicate between different locations or different computers.
But it's like a communication between different...
Yeah. Basically, just imagine it as a telephony network that uses quantum computing.
Well, do you think that everything's going to go over to quantum at some point, like in 200 years in the future?
I never thought of that, to be honest.
At the moment, I'd probably say no, but then there's the large list of quotes by people in the early computing field saying how no more than 2 people ever want a computer. Yeah. So I don't want to be one of those people. At the moment, the advantages the quantum computer give for very specific and often scientific problems, and we have incredibly powerful classical computers, but that's speaking from a very early stage, so I don't know what we'll be able to do in 200 years' time.
Okay, Ben, what do you think?
What do I think? Seems to me like it will just be another important tool in our analytical toolkit. We might be able to use quantum computers to make better quantum computers, ones that don't require you to freeze them down to nearly absolute zero. You might be able to use them to make better materials and high-temperature superconductors, and then all sorts of things will become really efficient, like energy transmission and energy storage, and who knows, this might be the key that unlocks a whole bunch of really cool technology.
I thought it was interesting, Katherine, you said that one of the quantum computers uses diamonds, and I think that's really interesting, like the idea of using crystals and crystalline structures to store data, versus what we've been using. Do you think that that is something that is going to become, like, we're going to see that more at some point? Are people going to start utilizing crystals and shit for computers?
Well, a semiconductor is just a crystal. And computers are already full of crystals.
I want some Superman crystals, you know what I'm saying? It's like a crystal and you plug it into something and then it goes. Like, is that ever a possibility? This is just for my personal happiness.
Unfortunately, the diamond system isn't that simple. You're trying very hard to isolate a particular defect or fault in the diamond. I've never seen one, so I'm not 100% sure what it looks like, but unfortunately it isn't plug and go. But I also love that idea. It would be shiny.
I know, it'd be much more accessorizable. It'd be way cuter. Broader strokes. Like what does the quantum computer mean for humanity? Like what does it mean on the bigger scale?
One application for quantum computing might mean that we are more efficient because it can do all sorts of calculations simultaneously. It can solve all sorts of problems, potentially, where we are currently really inefficient, like finding things and how best to do things in what order. And so, maybe it'll be the trick to us being a society that's less mean to its bike couriers or something.
So this is what I'm hearing. I'm hearing that the quantum computer could solve world peace. Could just be like, you know what, we got logistical problems with how to feed all these people because people keep having babies and it's crazy. There's just too many people on the planet. So you're telling me that a quantum computer could potentially help us figure out how to logistical problems for a world, if you on a humanity scale versus how do we take care of our people in a city? It'd be how do we take care of the world's people? It could do stuff like that potentially.
Maybe those are tend to involve computationally hard problems, so it's possible that the quantum computer might be able to solve it.
Okay. All right. I'm in. I like the quantum computer even more now. All right. Anything else? Any other weird stuff you guys can think of that help us to how could the quantum computer help humans evolve? I guess that's a better way to put it.
I think if you go back to the 1920s and ask them to imagine life today, you're probably not going to get anyone even managing to imagine that you can carry around your phone and look up information instantly on it and access information from around the world. Nearly all academic journals, although behind paywall, you can access from your phone. I think the fact that you probably have access to nearly all of human knowledge in your pocket, I don't think they could imagine that. And in a way, I don't know whether we can imagine how the world will change with quantum computing, just like we couldn't imagine how the world changed with classical computing.
Going back to earlier, I do think it's interesting, though, that, the futurists and stuff are always predicting that we're going to merge with technology at some point. That just seems like an inevitability at this point. And I'm just really interested to see how the quantum computer could work into that, because I feel because it's weird, I don't know, humans are weird, and brains are weird, and consciousness is weird. And if anything's going to, mesh with us, it'd be something else that's weird. And the quantum computer sounds really bizarre.
One thing I like, and I don't actually know if you can do this with classical computing, and it may be possible, is what they're working on in quantum computing is the idea of cloud computing where the central computer doesn't know what calculation you're doing. So you still, although you're using a central computer at a central location run by someone else, you still have complete privacy on what you're doing, what task you're doing, and what you're using your computer for, and what data you're sending.
I like it.
And I think that's a useful application, but there may, I don't know enough about classical computing to know if there's a classical way to do that, but I do like the idea that you can have, because cloud computing at the moment, I don't like the idea of the central database. The person at the database knows exactly what you're doing, so that's security. But there may be applications in classical computing for that as well. I couldn't say, but that's something I like.
So it'd be kind of like a mother brain, but except having like a, hive mind thing. We'd still all be separate. Okay. That seems efficient. Like Ben was saying earlier, it just seems like it could make us a bit more efficient and, hopefully help us to think of more interesting and creative ways to solve these dumb problems that we have, in our society.